Time now to look at the second section of Chapter 3, which is measures of variation. Remember what this meant is if we're looking at our bell curve or normal curve, variation is sometimes called spread. It's telling us how spread out or how wide is this bell curve. So the key concept here is we're looking at, again, how spread out the data is. We have three main measurements that we use. Range, which is probably the most biased of those estimates. Standard deviation and variance, which are very closely related to each other. So these are going to be for numerical data, so we're not looking at any sort of qualitative data here. So first off, our round off rule, just like with measures of center, we round off measures of variation 1 decimal place beyond the data. So if our data only goes to the nearest ones or nearest whole number, we would round our variation off to a single decimal place. Some textbooks actually would say the measures of center go 1 decimal past the data, and measures of variation or spread go 2 decimals past. For this textbook, we're going 1 decimal place past the data. So our simplest measure of spread is the range. And the range is simply found by taking the largest value in the data set, the maximum, minus the smallest value in the data set, the minimum. So if I have a set of data here, we'll get to an example in a second. Actually, I'm going to jump down. So here's our set of data. We find the largest value, which is the 75. The smallest is the 20. We subtract to get a range of 55 minutes. Well, back to this slide here then. One of the weaknesses of the range is it's not resistant. It's not resistant at all. One really small value or one really large value is going to greatly change the range of the data. So because of this, because it only uses those two values, it's really easy for it to be thrown off because of those extreme values. So a little bit more reliable measure is something called the standard deviation. The standard deviation takes into account every data value in the data set. And what it's measuring is the distance of the data points from the mean. Now, symbolism here, notation. If we're looking at the standard deviation of a sample, it's just the small letter s. If we're looking at the standard deviation of a population, it's that Greek letter sigma. Our formula for sample standard deviation, it's slightly different for a population standard deviation. This is the formula that is standard in most textbooks. It's you take each data value, and from that data value, you subtract the mean of the data set. Then you square it, square that difference, and add those all up. Then you divide that total by n minus 1. That would give you the variance, by the way, and then take a square root. There's a shortcut formula down here, which we will explore later on. So some properties of the standard deviation. Just like the range, but not as sensitive as the range, standard deviation is not resistant. One really small or one really large data value can have a big effect on the standard deviation. What the standard deviation is measuring is, I don't want to say average, but the mean distance of the data points from the mean of the data set. So it's basically saying how far the data points are from the mean. It's deviation about the mean or away from the mean. Larger values of the standard deviation, larger values of S, indicate greater amounts of variation, so wider bell curve. Again, not resistant to outliers. Really small, really large values will change it a lot. The units of the standard deviation are the same as the units on our data. So let's say we're measuring hours of sleep in a night. The units on our standard deviation is going to be hours. The sample standard deviation, though, is a biased estimator. So a biased estimator. Let's step back and talk about what is an unbiased estimator. An unbiased estimator would be, you're going to have data points here from our samples. The center of those is going to be the population value. That would be an unbiased estimator. Well, as a biased estimator, we're saying we get all these different sample values. The center of those sample values will not be the population standard deviation. It's a slightly offset estimator. So let's look at calculating the standard deviation here. So the first step is to find the mean. So we're finding the mean of our values for this data set. So we add them all up and divide by n equals 11 here. There's 11 data points in that set. So we divide by 11 and get our mean of 39.1. The next step then is to subtract the mean from each data point. So 50 minus 39.1 gives us 10.9. 25 minus 39.1 gives us negative 14.1. And we do that for every data point down there until we get these set. These are what we would call the deviations from the mean. That's how far each data point is away from the mean. Step 3 then is to square each of the deviations. So we square each of those values. 10.9 squared is 118.81. Negative 14.1 squared is 198.81. And again, we go down the line doing that. Once we have squared all the deviations, then we find the sum of those. In this case, they all add up to 2,740.91. And then it's very important we divide by n minus 1. So n equals 11 here because we had 11 data points. 11 minus 1 equals 10. So we're going to divide by 10, giving us 274.091. Now this is actually what we would refer to as the sample variance. To get the standard deviation, we still have to take the square root. We take the square root of the 274.091. We get 16.556. Remember, we round to 1 decimal point past the data. Since all of our data points were given to the nearest 1, we round to the nearest 10th. So our standard deviation is 16.16 minutes. If we wanted to use the shortcut formula, it looks like this. Now, I'm going to kind of quickly go through and show you where each of these numbers came from here. So this one here, the sum of the x squared. So I'm just going to go to an Excel spreadsheet here. These are my data values. The x squareds, I'm going to take each of those points and I'm going to square it. So 50 squared is 2,500. 25 squared is 625. Go all the way down the line to 20 squared is 400. Now I need to find the sum for each of those actually. The sum of the x squareds is going to give me 19,550. And I do need the sum of the x values, the actual values, giving me 430. We actually saw that when we were doing the mean, that the sum was 430 before we divided by 11. So that's where the 19,550 there comes from that. The 430 is the sum of just the x values. So it's n, which is 11, times the sum of the x squareds, minus the 430, which is the sum of the x's, squared. So 430 squared, so this is I'm just going to do equals 11 times the sum of the x squareds minus the 430, the sum of the x's squared, giving us the 30,150, which is exactly what we have at the top of our square root in here. And then on bottom, it's n times n minus 1. So n's 11, n minus 1 would be 10, so 11 times 10 is 110. We divide that out in square root, we get the 16.6 minutes. The shortcut formula was designed for being used with programs like Excel. However, Excel has a built-in standard deviation function. Now, it's important here that notice I wrote standard deviation of a sample. So stdev dot, notice there's two options that pop up over here, dot P and dot S. Dot P would be the standard deviation of a population. We're going to see in a few minutes that that formula is slightly different. We want stdev dot S. This is the standard deviation of a sample. When we hit our open parentheses, we just then, inside the parentheses, we highlight our list of numbers and close the parentheses and hit enter. And there it is. Notice we'd have to round that to 16.6 to agree with our rounding for our round-off rule. A third way of estimating, now this is not calculating the standard deviation, this is estimating the standard deviation, is something called the range rule of thumb. Because, as we're going to see here again in a few more minutes, something called the empirical rule tells us 95% of the data is within 2 standard deviations of the mean. So that means if we have our bell curve, and here's our mean in the center, if we go out 1 standard deviation to each side and then a second standard deviation to each side, 95% of our data is in that range. So only 2.5% is on each end of that, on each what we call the tails of that data set. Because of that, if we take a sample, our sample is taking less than 95% of the population, chances are that most of that sample is falling inside of that 2 standard deviations in either direction range. So you got 2 standard deviations on this side, 2 standard deviations on that side, giving us a total of 4 standard deviations. So if we simply take the range and divide it by 4, the range of the sample, not the range of the population, if we take the range of the sample and divide it by 4, we get an estimate. Notice it says estimating the value of the standard deviation. We'll get an estimate of the standard deviation there. Now, standard deviation of the population we mentioned is slightly different. The difference, everything in the formula is exactly the same except for right here. For a sample, it was a small n, which is the size of the sample, minus 1. For a population, it's a capital N, which is the number of items in the population, and there is no minus 1. We'll talk about why we do just n for a population and n minus 1 for a sample later on in this slideshow, but it comes down to degrees of freedom. If we're looking at a sample, if once we know the mean of the sample, well then once we get to most of the values with only 1 left, that last value is determined. It has to be the correct value to give us the sample that we've already calculated. So variance, as I said, variance is related to the standard deviation. It is the sample standard deviation squared. Or we just stop before we take the square root in that standard deviation calculation to give us the variance. The sample variance, just like the sample standard deviation, is the small letter s. Sample variance is the small letter s squared. Population variance then is the sigma squared. So there's our summary of our notation. If it's a sample, we use small s for standard deviation, s squared for variance. For a population, we use sigma instead of s. So important properties of variance. Now, just like the standard deviation, it is not very resistant to extreme values. A really small value or a really large value will change it greatly. The units on our variance are square units. So if we're again talking about hours of sleep in a night, the units on the standard deviation would be hours, units on the variance would be hours squared. Just like the standard deviation, the variance can never be negative. It's always going to be either positive or 0. The only way it would be 0 is if all the data values were the same number. That is also true for the standard deviation, by the way. The standard deviation is never negative. It can only be 0 if all the data points are the same value. Otherwise, it's going to be a positive number. However, different from the standard deviation, the sample variance is an unbiased estimator of the population variance, which means if I take a bunch of samples and find the variance of each of those samples, they're going to be centered around, if this line is the population variance, the values of those sample variances are going to be centered around that population variance. Whereas with the standard deviation, it was a biased estimator, which meant the population variant or population standard deviation was not the center of the sample standard deviations. So here's that discussion I promised you. Why do we divide by n-1 in the sample standard deviation calculation? It's called degrees of freedom, or assigned without constraint. Once we know the mean, and to calculate the standard deviation, we have to know the mean. Well, if we know all but one of the numbers, n-1 of them, the last one is automatically determined by the value of the mean and the total of those first n-1 numbers. If we divide by n-1, then the sample variance becomes an unbiased estimator of the population variance. If we use just n, it would become biased. It would be always an underestimate, or smaller than the population variance. So to show you here, this is a sample standard deviation. If this were a population, I would use equals stdev dot p. Oops, come on. And I highlight this. And you notice I'm going to get a smaller number because it's dividing by n instead of n-1. Because of this, it is always true that a sample should give a smaller standard deviation than a population. Not to mention the fact that there's fewer data points in a sample, which tends to give a smaller standard deviation as well. So putting together this mean and these measures of spread, especially the standard deviation, there's something called the empirical rule. We mentioned this a little bit earlier when we were talking about that estimating the standard deviation by dividing the sample range by 4. What the empirical rule states is if we know the mean and standard deviation of a data set, 68% of all the values are within one standard deviation of the mean, 95% of the data values should be within 2 standard deviations of the mean, and 99.7% of the values should be within 3 standard deviations of the mean. Now notice though, this says only if the data set is approximately bell-shaped. In other words, if it is approximately normally distributed, this will be true. If it's not normally distributed, then there's another estimator that we'll use for this type of thing. So what this is saying, if we have our mean in the middle, if we go out 1 standard deviation in each direction, we expect 68% to be in that range. If we go out a second standard deviation, so 1, 2 standard deviations, 1, 2 standard deviations in that direction, we expect 95% to be within 2 standard deviations. We would say that it's an unusual value to be outside of 2 standard deviations, but not an outlier. If we go out 3 standard deviations in each direction, we expect 99.7% to be within 3 standard deviations. Values that are outside of that, we would call outliers. So here's our example here. We have an IQ score with a bell-shaped distribution, or in other words, normally distributed data, with a mean of 100 and a standard deviation of 15. So what that means is we have a mean of 100 in the center. Our bell curve is centered. I did not draw that well at all. Our bell curve is centered around the mean. Standard deviation of 15, we go out 15 in each direction. So 100 minus 15 is 85. 100 plus 15 is 115. That's 1 standard deviation about the mean. A second standard deviation, well, we'd subtract 15 twice. 2 15s, or 2 times 15 is 30. So 100 minus 30 would be 70 going here. 100 plus 30 would be 130 going here. Doing the same, subtracting 3 15s, this would put us at 55 and 145. And that would be our 3 standard deviation limit. 99.7% of the data should be in that range. So we would expect that very few data points outside of that. With that idea of having a mean of 100 and a standard deviation of 15, what percent of the data should be between 70 and 30? Well, first we need to figure out how many standard deviations that is. If the mean is 100, that's 30 units away from 100. It's minus 30 to get 70. It's plus 30 to get 130. That's 30 units. 30 is 2 standard deviations, 2 15s. So that means we are 2 standard deviations on each side of the mean. Like I said here, that would be from here to here. 2 standard deviations means that we would expect 95% of the scores to be in that range. What if it's not a bell-shaped curve or normally distributed data? Well, Chebyshev's theorem summarizes all data. Now, the empirical rule says we expect it to be approximately these percentages, really close to these percentages. Chebyshev's theorem does not say that. Chebyshev's theorem says we expect at least this percent of the data to be there. So the formula is K is the number of standard deviations about the mean. It's 1 minus 1 divided by K squared. We expect at least that percent. So if it's 2 standard deviations away from the mean, that's 2 standard deviations, it's 1 minus 1 over 2 squared. So that's 1 minus 1/4, or 0.75, which is 75%. We would expect 75% of the data, at least 75% of the data, to lie within 2 standard deviations of the mean, even if the data is not normally distributed. 3 standard deviations, well, that's 1 minus 1 over 3 squared, which is 1 minus 1/9, which is 8/9, or 88.9%, or 89%. We expect 89% of the data to be within 3 standard deviations of the mean. So an example here, if we have that data set with a mean of 100 and standard deviation of 15 again, 2 standard deviations would be between 70 and 130. We expect at least 75% to be in that range. If it's normally distributed, of course, that goes up to 95%. From 55 to 145, that's 3 standard deviations. We expect at least 89% of the data to be in that range. So we know that the empirical formula is always going to give us a higher percentage of the data in the middle. But again, the empirical rule only applies to normally distributed data. So comparing our variation in different samples, there's a tool called the coefficient of variation. Now, a lot of textbooks have stopped using this coefficient. Ours is going to continue to do it. And all it is a ratio between the standard deviation and the mean. So for a sample, it's just S divided by X bar times 100 to turn it into a percent. For a population, it's sigma divided by mu. Again, it's just the standard deviation divided by the mean. And then times 100 to turn it into a percent. The round-off rule for the coefficient of variation is always just 1 decimal place. Once it's been turned into a percent. So it's just 1/10 of a percent is what we round off to. So for our measures of variation or measures of spread, big thing to remember is the standard deviation, the sample standard deviation, is a biased estimator of the population standard deviation. So what that means is we cannot just find a bunch of sample standard deviations and average them together, find the mean of them to get an estimate of the population standard deviation, because it's not an unbiased estimator. It's biased. It's off to one side or the other. However, the variance is an unbiased estimator of the population variance. So if we take a bunch of samples and calculate the variance of each of those samples, if we find the mean of those variances, it should be really, really close to the population variance. So that is the end of section 2. We'll come back in a bit with section 3.